So today I'd like to present the work primarily of the structural group that I lead of Foster & Partners, that is the work over the last 7 years. I found through this period that we've developed an approach which is particular, which has evolved from the way that I've worked before. And I want to talk through that. I want to describe the approach, and then I want to set out 4 points that I consider defines our design process. So we're a team of around 25. We're completely international. Around 90% of our team is from outside the UK. We work on projects solely within the practice, and we do these with the architects, the environmental engineers, and the other specialists within Foster's, as well as collaborators from all over the world. We work through all stages of projects, with around 75% of our staff time spent on projects that we deliver through to completion, often with a partner based in the country of the project. We have projects complete, under construction, or being designed all over the world, and about 90% of our work is outside the UK. So I'm going to try to set out what is our design goal when we design structures. And I find it easy when I try to do that to fall into value judgments or compliments, basically, ways of paying yourself a compliment when I'm trying to define a philosophy. So rather than do that, I'd like to explain it through a picture. But really, the overall idea is that we're seeking a design which has integrity and which is what I like to call inevitable. In other words, nothing can be removed. And this is my photograph to try to illustrate that aim. It's a photograph taken in Kensington Park in London, and it's around the Round Pond. And despite the fact that the path on the left is muddy and uneven, and the path on the right is well finished and well drained, and despite the fact there's a fence at the end of the path on the left, it's still become a route. And I've actually seen joggers on that route, which when you think that the whole point of jogging is simply to cover distance to get tired, I think wouldn't expect it. But in my view, it's the inevitable route. So that's really my manifestation of what I'm trying to talk about. So to the first of my 4 points for a manifesto for structural design. And my first one is commitment. My position is that commitment is on the basis upon which all further points can be built. The more attention spent on a design or anything else, the more potential there is for it to improve. Commitment's not necessarily the same thing as time. It's not enough just to work a very long time on something and expect a good solution to emerge. It's purposeful. So the distinction is in the intensity of the process, appraising different options regardless of where they came from or how long they took to develop. I'm quite interested in the notion of creativity and how that relates to commitment. And this is an example has come to, which I'd like to present to you, is from a book I read called How to Fly a Horse by Kevin Ashton. This is Mozart. You'll all be probably aware of that. And in 1815, a letter was published in Germany's General Music Journal in which Mozart described his creative process. And I'm going to read an excerpt, a very short excerpt from it, you'll be pleased to hear, to explain Mozart's creative process. Provided I'm not disturbed, my subject enlarges itself, and the whole stands almost finished and complete in my mind, so that I can survey it like a fine picture or a beautiful statue at a glance. When I proceed to write down my ideas, I take out of the bag of my memory. For this reason, the committing to paper is done quickly enough, for everything is already finished, and it rarely differs in paper from what was in my imagination. So that's the classic notion of creativity. A piece of music comes to Mozart fully formed as a whole. I almost had a picture of somebody in the bath here. It's sort of the idea that this fully formed composition has come and all he has to do is write it down. And it's been used by many writers subsequently to 1815 to talk about creativity. But there's a problem. The letters are forgery. Mozart didn't write like that. And in fact, in his other writings, in his real writings, he explains much more clearly that he worked. He, of course, was talented, and he had worked from a very, very early age. But nonetheless, he worked in a way that I believe I would understand. That is, he sketched out a composition, he revised it, he set things aside, he came back to it later, but there was no single uninterrupted stream of imagination that he could then write down into a fully formed opera. And that's really the point that I'm interested in about commitment. Just the attention to evolving a design. I want to show some of our projects now, and we make structural models. We make them out of cardboard very often, and we make them as skeletons. They're not the whole of the building, they're the skeleton of the structure. Maybe this is a good slide to show commitment as well, because I'm not going to tell you what time this picture was taken, but it did involve commitment to make all of those models. And we make most of our models at the same scale, around at 1 to 200. And we like that because what's interesting is you then get an idea of all of the different scales that you're working at in the practice, which of course is interesting, but doesn't change the amount of attention any single project should have given to it. So the first project I want to show you is the Canopy in Marseille. This was the first project that we started and finished inside the group as a project of our own. It's very small. It is 46 meters by 22 meters, and it's a single idea. It's just a single, very flat, mirror-polished blade beside the old port in Marseille, a piece of a larger landscape design. We were part of a team led by Michel Devine, the landscape architect. And our approach to this was, once you have an idea as simple and as singular as that idea, you must follow it through to every single last detail. Every detail must be minimized. So you'll see that we come to an edge which is a very thin edge. This is the plan. We have no structure around the perimeter because otherwise we'd have an edge beam. We have no gutter around the perimeter because otherwise we'd have a depth on the gutter. It's shallow and it's cut inside. It's brought inside from the edge, and we take our water down the columns. It's a portal frame. We have depth inside the structure that you don't really read because it's a curved top surface. And we spent a long time with the contractor, Eiffage, very committed contractor, to getting a flat surface. So this was prototype 1, partial success, completely unacceptable, basically. That's just, yeah, exactly. That just wouldn't work at all. That's simply welded plate, and that gets what gets variously known as the hungry horse look, or you see a rib cage on the back. So that was a no. We moved to the idea of a sandwich panel. This is, of course, with a honeycomb affixed to it. Quite a lot of issues about how you can get a honeycomb to have a two-sided flat, the manufacture of a flat face on the bottom side, and particularly by the time you finish polishing it around the edge, you get a rounded edge, and that you can see quite clearly here. You can see how happy I look about it, where the two panels come together. This, I want to show two parts about this. This is the solution that we finally came to, which is blue foam, highly rigid insulation with thin sheets of steel either side. But I also wanted to show the drip detail around the perimeter, because, of course, if you don't have a drip detail on a flat roof like this, then you have a very quickly mineral build-up on the underside. So we went with this. We built what looks, I hope you agree, exactly what we drew as the framework. That gives us a lot of opportunity to vary the adjustment of the panels on site because it's very accessible. We fixed the mirror underside. You can see how the edge comes. We like the fact that it looks like you've sort of chopped it out of the background, and we're very proud of the result. And one of the things that we find is very interesting about this canopy is, for all it's very present when you're underneath it, looking at it, when you get further away, it becomes more and more invisible. It becomes more and more part of the port without dominating it. The second project I want to show you is the Chateau Margot Winery, which is in the south of France. Again, a small project. And in this project, Margot is a premier cru in the Bordeaux region, and this is their first new construction for 200 years. So, of course, we had to respect the buildings around. We had to make sure that we fitted with them. We had to use the same tiles on top and the same angle for our roof. But that was a benefit for us. So really, as you're probably aware, a winery is an industrial space. You need a large, or in any case, free-span, flexible space to make wine in. You don't want trusses going across the middle of it. So if you look at my diagrams on the left-hand side of this slide, you show our simple move from making a long, deep beam at the top to where we ended up at the bottom. So with a deep beam at the top, we'd simply have a simple bending moment diagram from end to end. If we put support and a backspan into that, we can slightly haunch and get some hogging for our bending moment diagram and reduce it. And if we then angle upwards, and above all, of course, take axial load into the roof and therefore sideways cantilevering load into those trees, then we can effectively make a hinge if those vertical supports are stiff enough, and that brings our moments down again. And as a result, the beams that make up this diagonal grid are 360 millimeters deep across a span of around 23 meters. So quite a shallow span for quite a shallow structure for the span, and as I say, achieved by these tree structures. So I wanted to show a summary, a small excerpt of the number of different models studied for these trees, starting in the top left with one of the early sketches, and then moving across to the right. As you can see, we simply said, well, we need to pick it up at 5 points. We'll pick those 5 points up and go down to the ground. We're trying to do two things, of course. We're trying to resolve that force round and down, but we're also trying to resolve an inclined plane with a flat plane, which leads to complication. We didn't want to have a node. We did plenty of models with a big cast node and those 5 members coming into it, but we didn't want that. We wanted to make our trees out of flat plate. So no cast piece, everything out of flat plate. And you can see towards the bottom where that form is taking more and more the shape of its final form. And we worked, of course, very closely with both the architects and with our specialist modeling group to develop this. And this is the three-dimensional model that we finished with. We worked with Zela, the contractors who did the steel and the glass on this project, and sent this model to them, worked with them to develop it, and then sent the model to them. They made one prototype. First of all, you can see how proud they are of that prototype. And that was built on site to verify that this was the sort of scale that we wanted to build at. And then that was agreed. And having done that, Zela made the entire structure off-site and built, and then cut it, and brought it to site in sections, and then assembled it on site, re-welded it, and then it was finished and fitted out. And I find this view very interesting to see the underside. Of course, the laminated veneer lumber timber panels above are providing lateral torsional buckling resistance to the 360 beams. But I think this is a really interesting view of the space that's created. As you can see, a very flexible space. We have a moving crane. You can see that on the two sides. But a very flexible space that these fermentation tanks are placed within. So this is the final winery. And this is the tree as it finally turned out. A front view of the winery, where the grapes come to, where they're delivered, and a night view of the structure. So my second point that I want to put in my manifesto is technical knowledge. And in fact, some of my team, when I run this by them, said, I don't know what that is in first. And I think they might have a point, but I think that commitment is really the basis to start learning about all the other things. I don't think there's any substitute in engineering for technical expertise based on an idea, on structures from first principles. I think you have to have that basis of knowledge, and then you have to develop an expertise in the areas that you want to work in. Our ideas as engineers resonate if we have the understanding of how we would be able to deliver them. That's not the same thing as being immediately aware of the final solution from the first moment of conception. That's different. I think innovation can require research and time, the development of a solution, but we should have the understanding to know how we're going to approach the problem. So the team at Foster & Partners has really been built around technical expertise and has a particular knowledge in seismic and dynamic design, as well as the design of tall buildings. And this knowledge is complemented by partnerships with teams, with other firms all around the world. We welcome partnerships, we benefit from them, and we've had some very strong relationships with other engineers on projects. My first example, and our biggest project to date, is the Tocumen Airport in Panama City. This is a new airport extension to the existing Panama City airport for 8 million passengers to make a total of 15 million passengers for Panama City. This is a much larger model. This is 3.6 meters long because it's 720 meters long, and in an area of some seismicity. Panama City has some seismic activity, although when we went there and talked with some of the people who wanted us to sort of minimize the amount of seismic design we did, they said we haven't had an earthquake here for ages. But that, we said, doesn't really count. So we went ahead anyway and performed seismic design. And as I'll explain to you, we had to do some performance-based seismic design. So here is the internal view. And the idea of this, the idea of the roof, was to have a series of gently curving secondary elements which seem to float with the ceiling above the airport, just so that they just gradually vary in curvature down the length of the airport. So what we do is we place the columns in between the secondaries and the primaries, which you can see there, the rolled sections, the round sections, node, of course, for the columns, and then go through the center line of the secondary beams. So as a result of that, we don't node our columns on a secondary beam. And that means that we don't have a system which can be designed by a prescriptive code-based approach. In the American codes, we'd be designing to American codes in Panama. If you can fit with an existing system, or rather a prescriptive code agreed system, you can use the pre-qualified connections. We had to come up with a new series of connections. And in particular, we developed for this project a ductile fuse at the top of the reinforced concrete columns. You'll see in this diagram at the top the round hollow sections, the secondaries, which have a rainwater pipe going through them because there's a lot of rain in Panama and we needed to take it down at frequent intervals. And that goes right through the center of our column, which obviously is not ideal for the structure. We then come down and into this reinforced concrete column. And what we wanted to do was avoid taking seismic loads or extreme seismic loads in the roof. We wanted the roof to stay essentially elastic during a severe seismic event. And we've achieved that by introducing a ductile hinge zone in the reinforced concrete column. And you can see that shaded in blue. And in a slightly deeper blue, you see the reinforcement bars, which have been coupled to the larger bars to either side to have a smaller diameter in that area, which means that is the area which will undergo ductile movement, ductile extension in the event of an earthquake. This, the analysis and the calculations for this project were reviewed and approved by 2 independent international peer review teams, and the project was presented by Andrea Sologon at the 2017 ACI convention in October and will be published in their performance-based seismic design manual next year. So this is it's on site, the project's on site, the steelwork is now finished. This is the fuse clad in just straight out of being cast. It'll be slightly cleaner than that once we've finished. And this is work on site at the moment. That's the front drop-off area. You can see how those columns node in between the secondaries. Here's another view from up top, where again you see the noding columns coming into the primary beam, and that again goes through the secondaries. Another view, and we're putting the facade on at the moment. So this was the photomontage, which was the basis of the competition-winning design, and this is where the project is at the moment. We're just beginning to put the roof cladding on. The second project that I'd like to show you is a concept that we won, for which we won the competition for a new tower in New York, 425 Park Avenue. This is the competition-winning concept, which is now being built out by WSP, who are the engineer of record. We started as an integrated team on it, and I want to explain how we came to our solution. The volumetric rules, the planning laws in New York are extremely prescriptive about what towers can be built. The setbacks at various different heights define very precise volumes. So pretty quickly, the team were aware of what overall volume they needed to achieve and how that volume would be arranged. The next move was that the client was clear that they wanted, which we agreed with, cores at the back of the space, so that they got these optimum spaces in front, which look out over Park Avenue and have views of Central Park. So we start with this quite well-defined volume, and we worked through a lot of different options around this with the architects, and came to the idea that the single structure along the front, the single structural elements, the columns, perform all of the structural functions, both vertical and lateral stability, without the need for anything else, without the need for any hidden belt trusses or extra strength. So the best way I can describe this is on the right-hand side. You'll see that row of, well, the line of columns coming down the front. They then bifurcate once at the top level, and you can see that in the elevation in the center, and those are the axial loads gradually growing in red. And that, of course, transfers shear into the core, or between the core and the columns. They continue down the front again. They bifurcate again a second time to break that longer span in the bottom volume, and then the loads go down to ground. And the point about this is that as a result of that, all of the stability is achieved by that structure. And on the left-hand side, you see the, call it less critical, that is the wider side of the tower, where most of the stability is, most of the function of stability is performed by the core, and you can see just a little bit of the total overturning moment, that in blue has, there's a slight difference between the core overturning and the total, which is performed by that front line of columns. But more significantly, in the narrower axis on the right-hand side, you can see that the total overturning moment in blue, which obviously gradually grows towards the bottom, is substantially reduced in the core by the shear transfer at the top bifurcation of the columns. So as a result, that tower, the structure of that tower, does everything in a single move. There's no need for anything else to be added to it. The final project I want to show you is a tower that we're designing at the moment. This is in Mumbai. It's the Ocean View Towers, and the client is extremely clear with us. He would like a view of the ocean, and that is really his main priority. And as a result, all of the views of the apartments, of the main living rooms, must all look towards the sea. So you can see now there are two towers, and you can see there they are in plan, really a bar facing the sea with two cores, one core for each of those two bars. They're separate towers in this current scheme that we're working on. And we wanted to make sure that we maximized the views to the sea. So here is the view. We draw everything in BIM. This is drawn in Revit. We do all of our work in Revit. And this is our BIM model to show that tower. Now, I want to explain our logic in particular with our approach to this tower. This was the scheme that had been developed. The developer is extremely experienced, has a very clear idea of how they would like their apartments to be laid out, worked very closely with the architects to achieve this. And then we were discussing this with the architects and felt, as you can see, back it up. In the axis, in the up and down axis of this picture image, you can see that the core provides most of the stability. It has enough stiffness in that direction, but the core would not be strong enough to provide stability in the other direction. And there's a moment frame along that front bar, the front and the rear sides of the apartment block. That is a moment frame. We felt that that was very restrictive for the space, and so we made the move to remove those intermediate columns and of course the beams that go with them we want to keep, because then we make into long span beams which take us out to the corner columns. And in order to achieve this, we've added 3 outriggers over the height of the building. This is the critical direction where you can see under wind loads. There's mild seismicity in this area, not as severe as some of the other areas that we're working at the moment. So wind load is governing, and you can see there's a very healthy shear transfer across the 2 sides. On the right-hand side, that's the axial load gradually growing for wind load on one side, and you can see quite a decent shear transfer at each outrigger level. In the other side, there's also some shear transfer because we also connect with bracing between the front columns and our core in this direction too. So the result is something that we're very excited about. This is work in progress, very much still in the design stages, but we think that the towers are going to be extremely exciting at the end. Okay, so I'm going to move to our third point in my manifesto, and this is collaboration. Now, this title, I hesitated a long time as to whether it should be collaboration or communication, but I've gone with collaboration. Earlier in this talk, I considered creativity in terms of commitment, and in the case of collaboration, my view is that innovation can be considered in terms of collaboration. In other words, what is important in collaboration, if we can collaborate, if we can share knowledge, that's when we have the best chance of innovating. And whether that's inside a design discipline or across disciplines or with a completely wider sphere of knowledge, I think that most innovation comes from the transfer of technology, and most of that comes through collaboration and communication. So we have a lot of reviews inside the office. This is sort of deliberately picked to not look a bit untidy, basically, because we really do review things. We paste things up on the wall. Other people are sort of pushing past you to go and do something else. There should be a constant conversation about what you're designing, so somebody else may contribute something. We're interested in people meeting each other when they're at the canteen having lunch or having a coffee. There are, of course, formal design processes. We have a design board inside Foster & Partners who review all of the projects, but we think there's also a huge benefit in all of the informal reviews that go on as well. I want to show the Maggies clinic in Manchester, which is a new Maggies centre. Maggie centres have been set up as places where people who've been diagnosed with cancer or relatives of those people have a place to go and draw their breath, to gain information, but also simply to have a moment's peace. So they're supposed to be a gentle feeling. They're not supposed to feel like offices or surgeries. They should feel like a place that you walk into and calm down and don't feel like you have to answer to anybody. And so they're really a domestic feel. We started by thinking immediately about timber. This is a single-story building, very small scale, spans of around 5 or 6 meters. And we wanted to simply, if you look at the top diagram, have a spine of services. And down that spine would be the offices, it would be the administrative spaces, which should be private, and services, toilets and so forth, cloakrooms. the original idea was to say, well, we'll simply cantilever out on each side and contain underneath us what would be the effectively living spaces. And the discussion that we had internally, the design discussion was, by the time you've finished doing that cantilever, you'll spend all of your time designing a deflection head, which if you put something about the size of the mullion needed for the glass, you won't need to have. So we quite quickly got to a very useful discussion, and you'll see the second slide, the second diagram down, which was if you just have the slightest point in a structure as small as this, you'll take away the need for much more complexity and cost, because of course we're designing these projects on a very tight cost. There was then an additional piece added for these projects where the client wanted to have two levels, albeit open levels, inside that spine, so that there would be an open space on top where people could work but weren't cut off. They never wanted to have the idea that you had to walk down an office and take the third one on the left and look at somebody's name and knock and enter. Everything is open. And so you'll see on that third diagram down, we have a mezzanine, and therefore we come up and over that. And we've used that structure now to provide all of the lateral stability, as well as, of course, the vertical load-carrying requirement of the roof. So the bottom picture is where we've finished. We effectively have a portal frame for the lateral across the width of the building stability, and then the beams out to each side, which then cantilever out beyond the facade to provide sun shading, as you'll obviously be aware is necessary in Manchester. So what we've done is we've designed and optimized the structure so that we remove all of the material that we don't need. So you'll see that our cross bracing, the diagonal bracing for shear inside that truss gets wider apart where the shear requirement goes down. And in fact, the size of the flange members also gets larger and smaller according to the forces within it, obviously for the envelope of both lateral stability loads and vertical loads. So this is the diagram of this building that we come with. We want it to be extremely legible. We don't want you to come in and have any misunderstanding about where you're supposed to be. You walk in and you don't have to ask somebody for directions. It's just an open, inviting space. And we wanted our structure to be out of a material which felt good to the touch, soft to the touch, timber, but also would be cost effective. And we wanted to design it in something modern. We didn't feel the need to go back to or spend the expense on extremely expensive timber. So we use laminated veneer lumber, and we build it up in sheets. And we wanted to detail it. My feeling is that quite often in timber, it's quite hard to avoid. We wanted to avoid that phenomenon that you can get in timber, where the nodes dictate the size of the timber pieces. And because you're the hardest thing about timber is getting loads in and out of nodes quite often. So the timber can be quite big in order to contain the size of the steel plates and the bolts that you need to connect them. Slight simplification, but still it was an aspiration that we wanted to avoid that. And so we've tried to make our load transfers as direct as possible and not take all of our load out and into steel and back into it and back into the timber on the other side. And largely we've achieved that. So this shows you the manufacture. I'm sorry. This is Bloemen Lehman, who we work with very closely, and their engineers, SJB engineers, to fabricate these sections. They were fabricated and then delivered to site and assembled on site from prefabricated elements. We're particularly interested in that node, which of course is really the sort of pivotal piece where the loads transfer, and of course we don't need anything in the middle. Here it is being constructed on site. Went together, as you can imagine, extremely fast. There's the construction progressing, and there's the final internal space. And this is what we're trying to achieve. We're trying to achieve that thing where you can go up and touch it. And it's relatively rough, doesn't mean to sound pejorative, but it's something that you feel it, and it doesn't feel like it's not like the side of a violin. It's something which feels like real timber. This is the top of the spine. You'll remember I talked about the top space where people can work but are still visible. They haven't disappeared into an office. And they're in that space right up underneath the skylights. And here's that node that I was referring to. But you can also see the quality of the timber here. It's quite, call it industrial, the timber that you see here. And you can see the way that the diagonals get tighter where the shear demand is greater. Very little shear demand across the middle. And there's a view into the skylight. This is a view from the garden of the area where there was a particular area set up that people could work with, could tend plants as part of a way of just having a moment to themselves. And this is the end view. And this project won the 2016 Timber Awards Gold Award and the Structural Award. So we're very proud of that. And the final example I wanted to show you in this section was a museum of archaeology that we're in the process of building in Narbonne in the south of France. Again, the same model approach, made out of cardboard, and just there to show the structure. This is 20,000 square meters, built on a very tight budget, and therefore the structure is exposed. It defines volumes, and therefore we needed to make something which, for all it was built at a very low cost, we still were going to see it, and we wanted to see that it was appropriate in its quality. So the overall idea of the structure is a roof made out of prefabricated, pretensioned concrete T-beams, which sit onto a series of concrete beams, which themselves sit onto walls and down and into the ground. It's a mildly seismic area and a site which requires quite soft ground, and therefore required piles down into the ground and some analysis about the seismic behavior in that soft site. So here's the finished view of what the museum will look like, and you can see this large expansive roof. We wanted to build the walls in something which had something to do with the area. And these walls this is cementitious, so it is effectively concrete. It's not rammed earth because it has to take significant loads, seismic loads, but we've built it in a way which is a very, very dry mix, hand-tamped in layers 20 centimeters thick with additives, with colorings from the region, so that we get what we consider, this is what we set out to achieve. These are the architect's renderings for the competition, and this is the current progress on site. That's about 2 weeks old, the progress on site. So we're very excited about this finish that will be both the outside and the inside finish of these walls. They have insulation down the middle, and we had some interesting discussions, reflections about differential thermal effects across the thickness of these quite substantial walls and along their length. But the project is progressing very well and will be finished next year. Here's another picture of the underside showing the prefabricated reinforced concrete T's onto the beam and onto the wall beneath them, and there's progress on site. So one of the other things that we've worked with a lot, one of the clients who's very important to us and has been a huge input into the structural work, the structural team's work, is Apple. And we've had they're of course extraordinary designers. They have an incredible design reputation, and that's been an amazing experience for us. And we've built stores with them all over the world, and are very proud of them. And I'm not going to show you all of them because I want to only show you a selection of our approach. This is one of the first. This is Westlake in Hangzhou in China. And the particular point that was the architectural intention was to have this projecting mezzanine floor. That's a cantilever of around 12 meters, which tapers out at the end, and under which is another floor. And of course, on both of those floors, there would be the tables. Apple have these tables where everything is placed, and those will be on both floors. So there's a plan to show that model and a side view, and here is a cutaway to show the services integration. Really, the particular challenge of the Apple stores is, in addition to the technical challenge that each store poses due to its locality and to the ambition of the structure, making sure that we have a cantilever that we're happy with, is the tight integration of services, environmental services, air, lighting, sprinklers, water, with the structure. And that really has been a huge amount of work, a huge amount of concentration to get those working closely together. The lighting panels, I should say, were actually designed, they're an in-house piece of design, the lighting panels, and they contain all of the services behind them and can be removed to look at them. So we did a lot of analysis on the floors. We needed, of course, to put some tune mass dampers in to bring their response to something acceptable vertically. And here they are. They're about 1.2 meters deep at their stem. And they come out, they taper out to around about 20 centimeters at their ends. It depends on which store. There they are being preloaded. And there's the finished Westlake store. This is the photomontage of Apple Westlake, and this is the finished Apple Westlake. The next store, I want to show you two other stores, and the next one has just opened recently in Dubai, the Apple Dubai Mall. This is an additional. This is inside an existing mall, the most visited mall in the world in Dubai, an extraordinary place. And we have brought this new mall. That's the finished mall. This is what it was previously. And so, in order to achieve what was needed, we built out additional cantilevers from the existing structure. The engineer for the existing structure was WSP, and we built all of the new structure which fixed onto theirs. And so we needed to build and of course work with them to fix our new structure onto it. And you'll see there's a bottom level which is supported by a set of columns and therefore not particularly large, but nonetheless cantilevering. And then that top level, which those are around 10-meter cantilevers going onto the existing concrete structure, which wasn't, which didn't have 10-meter cantilevers on it before. So we designed a series of. It was actually quite difficult to find a place to fix those beams to through the existing structure. And you'll see these are the beams coming out. Now I'm up at that top level, and if I look directly onto the beam, we had to make ourselves quite a substantial welded plate section in order to get our macalloy bars, our post-tensioning macalloy bars, all the way through the edge beam. We strengthened behind the edge beam and then post-tensioned those cantilevering beams onto the edge of the concrete slab. So here's a view up from underneath. You can see those plates have now had their fireproofing attached, and then after that, the rest of the fit-out occurs. These are moving screens, and then we look down from that onto the. Those of you who've been to Dubai will be aware of it. The most extraordinary fountains in front of you, which play a show every so often. The final store I wanted to show you has also just recently opened in Union Square in California, in San Francisco, and also recently won the Structural Engineer of California Excellence in Structural Engineering Award this year. This is the Apple store in Union Square. We work with SGH on this, our partners in California, and you can see there are several challenges in this project. In particular, there is a cantilevering, once again the cantilevering mezzanine, but the entire structure, the entire floor structure, spans over a ballroom beneath it. So the entire ground floor is also suspended above a ballroom. So I'm going to just show you the construction of this. It was an extremely tight site to build in. Once again, the cantilever is being built and finished. And here is the front view of those and the view from the mezzanine floor. And finally, of course, you'll see this is where that big spanning structure is actually located. We need a pretty substantial truss to get from one side to the other of the ballroom. I wanted to show, in the spirit of trying to show integrated design, how do you show everything that went into this project, everything that got forced into what eventually looks quite neat, but inside it is absolutely full. And rather than showing you a picture of an iPhone or something like that, which of course is an extraordinary piece of design, we took apart the building and took all of the elements inside it and laid them out. And that's what they are. And this is the Apple Store Union Square laid out. And I just want to take some time, just in case that's not immediately clear to you what's there, to show you what's in. Basically, that's like a box which has been opened up. So right in the center, the two grey patches, the two grey rectangles in the middle, are the terrazzo floor only, not the floor structure, just the floor only. Then to the left of that is the glass and the glass framing, and then to the far left are the structural slabs, the concrete structural slabs, reinforced concrete for the ground slab and composite deck for the slab above, and the glass to the right-hand side, and to the far right, the cladding at the rear side. You'll see grass up on the, greenery. There's a green wall in a park that we renovated on the back side of the store. Then to the top, you can see the solar panels in the top left. Just beside those, you can see the roof structure. Those trusses, those tapering trusses are the roof structure. And then further across, you can see the MEP, that series of parallel lines. That's the air being delivered. And then to the far right, just beside the green, that's the furniture. Those are the tables. And then at the bottom left is the structure, the cantilevering mezzanines, and then the cladding beside it, the ceiling and lighting panels, and the trees. So that is an Apple Store. My final subject, the final point that I want to put forward for my manifesto for structural design is curiosity. And I consider that curiosity is the basis for making progress. I think we should be continuously questioning ourselves about our own subject, about other subjects, and I feel that I want to show two examples of where we've done that. We do that with our own review system, internal review, structural reviews, and also we give each other talks about things that we've learnt about. But we also look into little pieces of research. And I'm just going to talk you through a piece of research briefly that we've done, that we'll be publishing soon, which really just stemmed from conversations about projects that we were working on. This is a classic composite floor, as I'm sure you're all familiar with. That is steel beams with studs and composite decking above it. I've been involved in composite floors through the whole of my career, and they don't seem to have changed that much. There are some new products, but they haven't changed profoundly. And the conversation that we had internally was, how do we decide what our floor span should be? How do we come up with these numbers? And of course, there are often perfectly reasonable, often very logical reasons for those to be a particular span because of the site or the demands of the brief, offices, residential, of course. But if somebody said to you, what do you want your span to be? We thought that was an interesting question. And so we did some studies on that, and we had to set out, of course, some basis for these rules because otherwise everything floats. So we said, right, we're going to have primary columns, we're going to have columns at 9-meter centers and primary beams between them, and we're going to vary our secondary beams from sort of arbitrarily 7 to 30 meters and see what our design brings up. Now, structure, of course, same things that everybody here knows, is designed for strength and serviceability. Strength design, once you've decided on what your load should be, which is a subject I'm not addressing here, is a minimum design. You can't go below that strength design. You must achieve it. Serviceability design is either deflection or more often vibration. And it seems to me a shame that something which has met strength criteria should have either additional depth or additional material added for serviceability. That seems to me to be material added for nothing. So we were interested in will you ever have a situation where serviceability design has beaten strength design? And there are plenty of different ways of approaching this, but we looked in particular at vibration and footfall vibration. So this is a graph just to sort of set up our reflection of the harmonics of footfall vibration. So you can see the frequency of the floor, and you can see the largest harmonic, the biggest footfall force in red is due to your direct footfall, of course, around about 1.82 hertz. That's the biggest force you're going to put into a floor. Then there are increasing harmonics, which are far lower loads at larger frequencies. Then we looked at our floor design. As we increased along the x-axis our secondary beam span. And on the vertical axis are two things. On the left-hand side is the modal mass of the floor structure, say something like half the mass of the floor, it is related to the dead load of the floor, and it's the amount for each mode, and then the natural frequency of that floor on the right-hand side, the brown. And you can see that the modal mass goes up as the span goes up, because of course there's more mass being moved, and the natural frequency comes down as the span goes up, for the same reason, because you've got more mass. And we found that very interesting, because what that means is if you superimpose across that span, as the frequency falls, if you superimpose the dynamic force being put in by people walking on the floor, of course you get a sudden jump when your natural frequency goes low enough that you're in the first harmonic. You're exciting directly the first harmonic. And you see that with the dotted blue line suddenly rising at that long span, around about 1780 meters. Of course, the numbers at the bottom, please don't read these as though it's an absolutely precise number of 17.8. It's all dependent on the assumptions we made in our initial conditions. But what we're interested in is there's a low dynamic load factor at the beginning, and then that suddenly goes up when we get into the first harmonic. And when we then calculate the response of our floor for increasing secondary spans, this is what we get. That is the response of the floor, the acceleration, and as we increase the span. And what's interesting about this is when we have low spans, although we have very high frequencies, we have low modal mass, and so we're still getting excitation because of that low modal mass. Then gradually the modal mass increases, but we haven't got to the first harmonic yet as we work our way across. And then we suddenly get to our first harmonic, and then our force, our dynamic load factor, suddenly increases, and we once again get a very big acceleration. So I find that very interesting, because that says to me there's a spot, and of course it will vary for the different assumptions you make and the different cases about the actual dead load of your floor, the actual stiffness, and your primary span. These are all things that would need a particular presentation for them. But nonetheless, there's an interesting phenomenon, and this is the same graph plotted for different damping ratios, whereby we can get underneath our response factor of 4, which makes it a nice unresponsive office floor, at those long spans. This doesn't mean this is less steel mass than for a lower floor. What it means is the steel mass that you need for the strength design will fit the steel mass that you need for the vibration. You don't need to add any mass or depth to achieve the vibration serviceability criteria. And this is a final, slightly, there are assumptions in this that I would be happy to explain, but I wouldn't end up designing the floors as we've shown on the side. But what we've done is just plotted secondary beam depth. And all this is showing is secondary beam depth has to go up. I think we've gone slightly higher on that side than I mean to. We wouldn't go as high as that. But if we were minimizing mass, we'd need to go up with our depth until we get to that, I'll call it sweet spot of span, and then the depth will be the same both for strength design and vibration. So as I say, that's a short version of an exploration we did into curiosity. We will be publishing that, but it's just a little thought process rather than anything more. The final example that I want to leave you with relates to sustainability. Sustainability is something which basically I think the tide's rising on structural engineers, that while everybody else is reducing their energy consumption and getting far more advanced about the way they approach the environment, that makes the structural component of a building design more and more important in terms of the embodied energy of construction. In other words, when we're using enormous amounts of energy during the life of a building, and didn't really have as clear an understanding as environmental engineers have now of the ways of reducing energy consumption in a building, the structural embodied energy was relatively low. That, of course, has become far more significant relatively because everything else has dropped. And I'm looking for a way of approaching that in something other than either an immediate quantification, which I wouldn't be against as long as I knew what I was comparing it to. And of course, there are ways of calculating embodied energy and embodied carbon now. But I'm interested in it as a design tool. How would you just approach a design conversation to minimize the embodied energy of your structure? And this is a graph. It's from the Cambridge University Selector. This is a database of information, and I find it extremely interesting. This is a plot of cost of materials per kilogram, as it happens, although you can plot them according to lots of other things, compared with their embodied energy of consumption, of production, of primary production. And the particular point here that I find interesting is that, by and large, there's a relationship. In other words, if you take out outliers, which is generally materials which have a scarcity value or a brand value, so jewels obviously have a totally different value from their mass. If you apply this to bulk materials, commodity materials, in other words, a lot of building materials, then generally their cost is quite directly correlated to their embodied energy of production. So low-cost materials might be the ones which really only cost the cost of cutting them down and driving them down from a Scandinavian forest, for example, or digging aggregate out of the sea and washing it. Those are low-cost materials, whereas high-cost materials would be high-temperature processes like metal production, steel or aluminium production. So what I find so interesting about that is what that says is if you are minimizing the cost of the materials to go into your project, no matter what those materials are, there's a reasonably good chance that you're also minimizing the embodied energy going into it. The cost will act as a proxy for embodied energy. And I find that very interesting, and I'd like to pursue it further, and we will be pursuing it further. So to finish then, these are my 4 points, and I value any comments because I've now put myself out there and said it's a manifesto for structural design. Value any comments or questions about it. But these are what I consider to be important. And as I say, they've evolved in particular over the last 7 years through my work at Foster & Partners and with a structural group: commitment, technical knowledge, collaboration, and curiosity. I wanted to leave you with sort of a quick slide of some of the projects that I haven't been able to show you that we're very proud to have been involved with, which I'd be happy to talk through more. Any of them from Mexico Airport on the left-hand side, through to on the right-hand side that suspended structure in the middle is the Kerouin 2 new building, new development in Kazakhstan. So that's my final slide, and thank you very much for your attention.